In this module, we will be covering the basics of single-lane roundabout design and providing a demonstration for the design of one approach to a single-lane roundabout at the end. These first few slides will discuss big-picture considerations that will guide our thinking during design. Section 3.1 of GDOT's Roundabout Design Guide outlines the design process and workflow for roundabout projects following GDOT's plan development process. While the process extends from early studies through final plans, we are looking at the portion of the process from operational analyses up to the concept report milestone. Essentially, what we're looking to do is to identify and validate conceptual alternatives that meet the project purpose and need, fit the context, fulfill all of our performance goals, are cost effective prior to us entering into final design. We're looking to explore the design space, take into account the location and context and constraints, evaluating the various geometric requirements. Are there a certain roundabout size we'd like to have because of design vehicles that may use the intersection frequently? Consider the trade-offs. Are there competing interests and objectives at the intersection? Do we have pedestrians or bicyclists? And is the intersection also used by large tractor trailers? The larger dimensions for the tractor trailers often work against the safety and performance for bicyclists and pedestrians. So balancing those objectives will be important during this phase. We're working toward the validated concept layout. And one of the key points to recognize for this process is that this is an iterative type process. We're going to develop multiple alternatives, and we're going to go through several iterations until we arrive at that refined concept. And that's all part of the process, and that's how we improve our designs as we work toward final design. The guiding principles for roundabout design, we want to keep this in mind as we work through the design of our single lane roundabout. But some of the decisions we make during design, are also influenced by these guiding principles. Designers should strategically keep the performance objectives of safety and operations in mind and let them guide the selection of various design details. The overall design composition, how all of the approaches and the circle size fit together, and the resulting performance matters more than the individual dimensional elements. The initial selection of the roundabout size as well as the position and approach alignments play a large role in achieving these high level core principles: capacity and lane configuration. How many lanes do we need? Safety for vulnerable users. Do we have room for sidewalks or shared use paths around the perimeter of the roundabout? The performance checks, making sure that we have adequate deflection and low entry speeds, that our largest design or check vehicles are accommodated, and that we're providing adequate sight distance for each approach. If we were working on a multi-lane roundabout, other considerations would be entry and exit path alignments and entry and exit channelization. Another important high-level concept is practical design. Practical design, designers should be looking to optimize the circle size, location, and alignment of legs to promote balanced speed control on every approach and ensure efficient movements. But it's essentially design optimization with a greater emphasis on balancing cost with capacity and safety benefits, and this requires careful consideration of design trade-offs. Eliminating lower priority project design elements can result in lower cost and improved value without adverse effects on safety and capacity benefits. And the upper right corner is an example from Appendix A in GDOT's roundabout guide. And this was a roundabout that had been designed with several right turn bypass lanes, and they were able to review the operations. They determined that one bypass lane, the eastbound right turn bypass, was not required. They were able to revise the geometry for the northbound right turn bypass, and as you can see, if you review the appendix, they were able to reduce the overall footprint of the roundabout without negatively impacting the performance goals, the operation and safety of the proposed roundabout. And in fact, in a lot of ways, they've improved upon the original design. So practical design, is important to keep in mind that it does not compromise safety. It does not eliminate design standards. It doesn't look to cut corners on standards, and it does not take the place of good practice. Uh, we want to follow those good design principles. Uh, it does focus on context. It does focus on purpose and need, on eliminating nice but unnecessary items, and it emphasizes the importance of engineering judgment. And so, in summary, practical design investigates the lowest cost of construction that produces the optimal, functional, constructible, and serviceable installation. And now we'll turn to roundabout design considerations, the nuts and bolts of the single lane roundabout design, and the key points that we'll hit on in this discussion moving forward are design and check vehicles, circle location and approach alignments, roundabout size and shape, approach roadway design, and entry curve geometry. The first of the 5 design considerations we will discuss are design and check vehicles. We won't go into depth into truck considerations here. We just want to note that thinking through design and check vehicles early in concept development is important because they play a role in determining many of the geometric parameters of the roundabout. It could affect the circle size and shape, the travel lane widths or the circulatory roadway width, and truck apron dimensions, just to name a few. It is important to perform field observations and review classification counts, land use, site context, functional classifications, and permitted load records in identifying appropriate design and checked vehicles. It may also be helpful to interview stakeholders near projects to identify other unusual design vehicles like large farm equipment. It is easy to accommodate very large vehicles during the design phase, but much more expensive to retrofit after a roundabout has been constructed. Once the design vehicle has been determined, the next step is to consider where the circle should be and to determine approach alignments. Before we look at examples, consider these rules of thumb related to circle location and approach alignments. The circle location should optimize visibility and low entry speeds for every approach. You may need to shift the circle to address skew or other constraints. The legs should form equal angles around the roundabout whenever possible, and try to utilize existing features to reduce costs or develop new geometry to help save costs. An example might be shifting a roundabout off alignment to simplify traffic control and maintenance of traffic during construction, making it easier to build more quickly while reducing the overall cost of the project. An example of how this approach can be applied is a dog bone roundabout in the middle of a commercial district in Bend, Oregon, shown on the screen. This is a one-way couplet. The southbound roadway is on the western side of the dual roundabouts. The northbound roadway is on the eastern side, separated by 300 feet. There's a variety of hotels and commercial restaurant hubs all along the east-west roadway in this area. And the dual roundabouts are situated at the ends of the one-way couplet and together serve to create a low-speed, pedestrian-friendly environment in the middle of town. Next, we'll turn to several examples of circle location and approach alignments. Skewed intersections can create challenges for roundabout design just the same as they do for other types of traffic control. As illustrated in the figure in the upper left corner, acute angles between approach legs can make it difficult for tractor trailers making right turn movements, while obtuse corners present challenges for speed control for passenger cars. While some intersections may allow approach realignment, site constraints may preclude this at other locations. Therefore, a variety of combinations could be considered at skewed intersections related to the size, the shape, the placement, and approach alignment. This might include the use of right turn bypass lanes as shown in the lower left, elliptical shapes, lower middle, or even too closely spaced roundabouts as in the lower right. Closely related to skewed intersections, we face a number of other odd alignments in real life, including T intersections, Y intersections, and closely spaced but offset intersections. For T intersections, it is usually desirable to center the roundabout on the existing intersection to provide balanced speed control and visibility for all approaches. If site constraints prevent this, then shifting to one side may need to be considered in conjunction with realigning the mainline approaches in order to achieve speed control. Pushing the roundabout to one side may provide advantages from a property or constructability standpoint. However, it can make the intersection less visible to drivers approaching on the main line. The site context should be taken into consideration whenever we make these kind of decisions. For Y intersections, a lack of speed control is a common issue due to the large angle between the legs. Realigning legs utilizing a smaller inscribed circle diameter or a combination of both are options to explore. For locations with closely spaced but offset intersections, options to explore include too closely spaced roundabouts, realigning one leg, or realigning both legs. The overarching theme for all of these scenarios is that the roundabout size, placement, and approach alignments work together as a three-legged stool. Adjusting one of these elements may require adjusting the others in order to maintain a balanced design and to meet design objectives. Next, we'll turn to consideration number 3, circle size and shape. A good starting point for a single lane roundabout is an inscribed circle diameter of 130 feet. The ICD may be increased or slightly decreased to accommodate right-of-way, design vehicles, or to control speeds to meet fastest path requirements. For 90-degree intersections that need to accommodate a larger design vehicle for every movement, for instance, at a state-to-state intersection, a good range for the ICD is 130 to 150 feet. In situations with more than 4 legs or skewed intersection angles, larger ICDs or different circle shapes may be necessary. The choice of a compact or conventional single-lane roundabout is dependent on factors such as space available at the intersection angle, the roadway classifications, posted and design speeds, and design vehicles. A smaller ICD has trade-offs related to accommodating larger design vehicles. Typically, a compact roundabout will not accommodate a larger tractor trailer, say a WB62 or a WB67, without over-tracking the outside edges of pavement or curbs. A lot of times we accommodate these larger vehicles at small circles using raised truck blisters or outside truck aprons. to compensate for the smaller ICD. In terms of roundabout shapes, obviously circular shapes are the most common seen with roundabouts, but there are also a number of elliptical roundabouts, teardrops, peanuts, and dog bones. An ellipse is typically beneficial where major roads intersect a minor road at a skew angle where it is difficult to place a regular circular shape within the constraints of the project. An ellipse is practical for separating the approaches for truck turning movements and to control entry speeds. The smaller radius of the ellipse should be placed into the quadrant of the acute angle as shown above. Peanut roundabouts are typically applicable at too closely spaced intersections that cannot have regular circles without overlapping. They can also be used at extremely skewed intersections or where right-of-way is constrained. A barbell or dog bone are other names for an elongated peanut that is spaced further apart than a peanut-shaped roundabout. They are used when two intersections are in close proximity, but there is a benefit to having a tangent connecting the two individual circles. And teardrop roundabouts do not allow for a continuous 360-degree travel around the circulatory roadway, and GDOT's preference is to use teardrops only when needed for operational reasons. The fourth major design consideration discussed in the GDOT Roundabout Guide is approach roadway design. Good approach design incorporates several principles, including offset left geometry, stopping sight distance or forward sight distance to the entry line, central island visibility, and the use of curb and gutter to help create a funneling effect as motorists travel toward the roundabout. GDOT recommends offset left approach alignments to promote gradual speed reduction and yielding at the entry. Offset left alignments typically deflect entry paths and help to achieve slow entry speeds. For additional information on offset left design, see NCHRP Report 672, Sections 6.2.1 and 6.7.1. Additional advantages to offset left design are that it increases deflection and it's best for speed control in higher speed rural settings. It maintains or helps to maintain clear sight to the central island. It's beneficial for accommodating large trucks because it allows for larger entry radii while still providing adequate deflection and meeting speed control goals. It allows designers to work with smaller circle diameters without increasing impacts because the offset left geometry allows us to reduce speeds to a greater degree. It may increase the exit radius, which reduces control of exit speeds and acceleration, but it improves stopping sight distance to the exit crosswalk. Although not preferred, radial approach alignments can be used on projects involving right-of-way constraints, those with alignment concerns, or in low-speed environments, and/or on low-volume approaches. The approach geometry should provide adequate forward sight distance to the crosswalk and the roundabout entry based on the appropriate design speed, whether it's offset left or radial design. In addition, the horizontal and vertical alignment should work together to make sure that the central island is as conspicuous to approaching motorists as possible. Section 3.10 also provides guidance for the design of high-speed approach roadways. In addition to the offset left geometry and the central island visibility that we talked about on the last slide, we are interested in reducing the high free flow speeds to low roundabout entry speeds in higher speed rural settings. It is good practice to use chicanes or successively smaller radii for reversing approach curves to gradually reduce speeds on high speed approaches. Within the transition or deceleration zone of a roundabout approach, Horizontal curve radii and K values for vertical curves should be based on the speed contour closest to the center of the curve, as shown in figure 3.10. You may notice that there are tangents between the reversing curves, and these tangents should preferably be the length of the design vehicle to minimize swaying of large truck loads and the loss of control roadway departure crashes that are sometimes seen at roundabouts that lack these tangent sections. Stopping sight distance should be preserved when adding reverse curvature, and this is necessary both horizontally and vertical. You may have seen chicanes that were a little overdone with extensive reversing curvature, and the forward sight distance of the road is actually cut off by the splitter island on the approach, and we're looking to use gentler chicanes so that we can maintain that forward sight distance to the entry line. Splitter islands on higher speed approaches extend upstream of the yield line to the point in which entering drivers are already decelerating. Practical design considerations for splitter islands suggest that for 45 miles per hour and above, we should consider 200-foot long splitter islands or longer. 35 miles per hour to 45 miles per hour, 100-foot long splitter islands should be sufficient, and less than 35 miles per hour, 50-foot long splitter islands are appropriate. The nose of the approach end of the splitter island should incorporate a 2 to 4 foot offset from the face of curb to the paint line as cars approach the roundabout. And section 3.10 and appendix C of the GDOT roundabout guide include additional discussion pertaining to the super elevation for the design of the approach curves. GDOT notes the idea of the visibility package, and they prefer to ensure that the signs, pavement markings, raised pavement markers or delineators, and landscaping on the approach serve to reinforce the speed reduction or the need for motorists to reduce speeds. And a good visibility package can sometimes compensate for shorter length splitter islands. Curb and gutter also helps vehicles to maintain lane discipline and reduces speeds, and therefore introducing it in the transitional and low speed sections of the approach is encouraged. The fifth and last of the design considerations is entry and exit design. Figure 3.11 in the slide illustrates a typical layout showing roadway dimensions for entries and exits. The right side curve near the roundabout entry, also called the entry radius, helps to control entry speeds and is typically between 65 to 100 foot. A rule of thumb for entry radii is to divide the inscribed circle diameter by 2. The left side radius along the truck apron can be larger since it doesn't affect entry speed control, but it can be influenced by truck swept paths. The lane width may flare at the entry if necessary to accommodate large trucks, but we want to hold the right side curb line to maintain good speed control. We add lane width by reducing the width of the splitter island slightly. The figure does not provide a range for radii on the right side of the exit lane, but common practice is to use exit radii between 150 to 500 feet. Smaller radii may be appropriate where there is pedestrian traffic or constrained right-of-way, and larger radii may be appropriate at locations with significant truck traffic. In terms of lane widths, typical widths vary between 16 feet and 20 feet for entries, exits, and right turn bypass lanes. This amounts to 20 feet to 24 feet from face of curb to face of curb if we assume that each side has 2-foot gutter pans. Note that in locations where we have curb or islands on both sides of an approach, designers should review Table 327 in the AASHTO Green Book to identify pavement widths that accommodate the design vehicle and allow for passing of stalled vehicles. This is especially critical for approaches with very long splitter islands. And that ends the discussion portion of this presentation. And from here, we'll move on into the sketching of roundabout approaches for a real-life demonstration. For this portion of the module for single-lane roundabouts design basics, we'll be running through a sketching exercise to evaluate the size and location of circles. We'll then wrap up this module by developing line work for one approach to a single-lane roundabout. The aerial map on the screen depicts an intersection and site characteristics and constraints for the purposes of a hypothetical demonstration. North is assumed to be to the top of the screen, and the right-of-way widths are assumed to be 80 feet in width for the east-west roadway and 100 feet for the north-south roadway. There are utility easements along the north side of the roadway that are 50 feet in width, and these contain aerial electric lines. If I zoom in, you can see the filled circles are high voltage poles, and the empty circles are more standard traditional utility poles. The posted speeds are 50 miles per hour for the east-west roadway and 45 miles per hour for the north-south roadway. The land use is agricultural in the northern two quadrants and residential and institutional in the southern quadrants. Both roads are classified as urban minor arterials, and the design vehicle is WB67 for this roundabout. There's a potential for residential development in and around the intersection, so pedestrian accommodations are deemed appropriate. However, bicycle provisions were deemed to be not necessary at this time. So based on previous capacity analyses that were completed earlier, we can assume that this will be a standard single-lane roundabout without right turn bypass lanes. As we discussed earlier in the module during the PowerPoint presentation, Table 3.2 in the GDOT Roundabout Design Guide provides ranges for single-lane roundabout diameters. In the context of our hypothetical project, we're in a rural setting or a transitional area between rural and urban land uses, so we would likely choose a conventional single-lane roundabout as opposed to a compact or a mini roundabout. According to Table 3.2, we would be looking at a range between 120 feet in diameter to 160 foot diameters. The approach legs intersect close to 90 degrees, so a circular shape makes sense here. There's really no need to look at ovals or any other alternative shapes. For the most part, our various alternatives will involve exploring different circle diameters and circle locations. Now, because we'll need to accommodate WB67s, let's choose 130 feet diameter and 140 feet diameter roundabouts as starting points. And perhaps we'll put the 140 foot diameter in the center of the intersection, like so. And perhaps we'll try shifting 130 foot diameter a little bit to the north to take advantage of the utility easements on the north side of the east-west road. And so these are the locations for the two alternatives. So for the 140 foot alternative, if we happen to lay this in, this is what the concept might look like. You'll notice that the right-of-way impacts are balanced in all four corners of the existing intersection. and it's primarily due to the roundabout curb and the sidewalk in each quadrant. But you also note that even though we introduced chicanes along the high-speed roadway, it's contained within the existing right-of-way on all four legs. So primarily our right-of-way impacts are limited to the four corners of the intersection. The small circles are utility poles. The filled circles are the high voltage, and the empty circles are standard utility poles. And you can see that we impact 6 standard poles, but we avoid impacts to the larger high voltage poles. Now, if we magically turn on the 130-foot diameter, this is what that circle might look like. Let me delete that circle. You can see the right-of-way impacts have been shifted to the north, primarily into the northern 2 quadrants in the easement area, and we've stayed within the right-of-way for all intents and purposes on the southern quadrants. Now, to accommodate the shift of the roundabout to the north, you'll notice the approach alignments on the east-west roads have also been shifted to the north. We're maintaining the chicane for speed control, but that will also result in more right-of-way impacts in the easement area along both approaches. So in addition to the right-of-way impacts in the corners, we're also going to we're chasing right-of-way impacts down the 2 approaches. And you'll also note that we're still impacting all 6 of the traditional or more standard utility poles, but now with this alternative, we're also into one of the high voltage poles, which can be pretty expensive to relocate. Now, this is an interesting example where smaller roundabouts result in more impacts than a slightly larger alternative. Presumably, both alternatives would be further refined to reduce impacts and costs to the degree possible. And we would also look at other factors like constructability, stormwater needs, and environmental and cultural impacts as well. So this completes our discussion of circle size and location, and next we'll begin sketching the west roundabout leg, assuming the 140-foot diameter circle centered on the existing intersection. To begin sketching the western leg of the 140-foot diameter roundabout, I've taken the liberty of drawing in the roundabout a 20-foot wide circulatory roadway, a 12-foot truck apron, and the center line of the western leg. And for this discussion, I'll be referring to several figures from GDOT and federal guidelines. And these include Figure 39A, Figure 3-10, and Figure 3-11 from the GDOT Roundabout Design Guide, Tables 6C-3 and 6C-4 from the MUTCD, and Table 313 from the AASHTO Green Book as it relates to the superelevation illustrated in Figure 310 for the approach roadway. Now, you may recall that the western leg was posted at 50 miles per hour, so we can assume that the design speed is 55 miles per hour for this exercise. And we'll begin by developing the left side of the approach roadway through the chicanes in the approach zone and then the deceleration transition zone. So we're looking to develop the left side of the roadway as we approach the roundabout, the right side of the splitter island through the chicane. And that's what we'll be looking to start with now. The end of the deceleration zone is at the approach side of the crosswalk. So if I go back to the figure, you see that the end of the deceleration transition zone is right before the crosswalk. The crosswalk is usually 20 to 25 feet from the edge of the roundabout. And depending on how wide your crosswalks are, you may be 30 to 40 feet from the entry line. So for the purposes of this exercise, I'm going to delineate the end of our deceleration zone by offsetting the edge of the roundabout by 35 feet. I usually develop chicanes about 1 lane width wide, and lane shifts to develop the chicane can be set symmetrical around the center line, or they can be shifted to one side or the other. For this demonstration, we'll shift the approach roadway 12 feet to the right, and there's no set dimension on the shift to my knowledge. That's just personal preference and how I often start my layout. So I will offset the center line by 12 feet, and that will be the largest extent of the chicane as we develop the approach roadway. Taking another look at figure 3.10, we see that the point where speed should be decelerating through 35 miles per hour, or approximately 225 feet from the end of the deceleration transition zone. So that 35-foot line that we just drew. So I'm going to offset that 35-foot line by another 225 feet. And this represents the point where we'd like to be around 35 miles per hour on the descent. Moving to the approach end of the chicane, we have the option of either doing a straight line taper or inserting a horizontal curve to move the approach roadway from the existing center line over to the right. And I've chosen to do a straight line taper. Referring to the tables from the MUTCD, we know that for speeds over 45 miles per hour, the length of the taper is equal to W times S. In this case, it's 55 times 12, or 660 feet. And the shifting taper is at least 1/2 L. So 660 feet times 1/2 equals 330 feet. So I'm going to offset this line by another 330 feet. And this becomes the beginning of our chicane, where we start moving the approach roadway to the right. If you recall, we would like to have offset left geometry. So as a ballpark, I usually start by offsetting 10 to 20 feet. In this case, I'll choose something in the middle, and I'll do I'll put in a radius of 15 feet, and that'll be, we want to line up tangent to that to develop our offset left approach alignment. So if I connect these points, we'll start at the beginning, the 35 mile per hour line, and then we'll come in on our offset left approach. And it looks something like that. Now I'll clean up some of these lines just so we can see what it looks like. Jumping back to figure 310, we see that the radius at the 35 mile per hour point should be 510 feet or greater. And that's to meet the minimum radii and super elevation for low speed streets in urban areas. So we'll go back and we'll try a 510-foot radius at this location. And see how that looks. Now, you'll notice you can barely see this curve, and it turns out it's only about 60 feet long. So we know we want our radius to be greater or no less than 510. What if we try 1,000 feet just to get more of a substantial curve in this location? Let's see how that looks. 1,000 feet. Okay, so that looks a little bit better. That gives us a curve approximately 118 feet long, so that's a little bit better. So that's the left side of our approach roadway through the chicane, including the curve, and the next step is to lay in the right side approach lane. Now that we have the left side of the approach roadway laid in, we can begin developing the splitter island envelope and the entry and exit lanes for the roundabout. Trim that up. Now we know that this line is the left side of the approach roadway or the right side of the splitter island envelope. I'm going to assume that at the roundabout or near the roundabout, our splitter island is going to be approximately 15 feet wide. That's just based off of my experience. If we were looking at this under a practical design microscope, we may reduce that to 10 feet so that we have a 6-foot minimum, uh, 6-foot minimum width splitter island. Um, in this case, I'm going to assume 15 feet, and that's more or less just a personal preference. Similarly, I'm going to tie that line in with a 2,000 foot radius, and I'm just kind of selecting that arbitrarily, but to tie in the left side of the splitter island envelope or the left side of the exit lane. We know that 1,000 feet is more than twice what we, or about twice what we need for the 35-mile-per-hour zone. Similarly, they'll be accelerating out of the roundabout, and you could conceivably choose a larger radius if you want to avoid the need for any super elevation. For the purposes of this demonstration, I'm just selecting 2,000. If we review figure 311, it shows us that we would like to have 20 to 24 feet in width at the mouth of the splitter island. And this also references table 3-27 from the AASHTO Green Book. And that relates to provisions to pass a stalled vehicle, and it on curved roadways, and it is contingent on the size of the vehicle and the size of the vehicles that you would like to pass. In this case, we can assume that width should be, the face of curb to face of curb width should be 18 to 20 feet in width as a minimum, whether depending on whether you choose case B or case C in that particular table. So we'll assume the 20 to 24 feet in curb to curb width as a minimum. So we will offset, I'll begin by offsetting this line 18 feet with the 2-foot curb and gutter on the outside. That will give us 20 feet to this painted line, and then there'll be an offset to the splitter island. So we'll have that 18 feet gives us that 20 to 24 foot dimension that we're looking for. We'll offset the exit side as well. To develop the entry curves, you may recall from the PowerPoint session that a rule of thumb for some designers is to choose 1/2 the ICD for the entry radii. I typically start with 90, and then I add the entry lane width or the circulatory roadway width to that 90 in order to develop my entry curves. So in this case, I'm going to offset or insert a 90-foot radius into the roundabout. And because our lane width, we would like it to be around 20 feet, I'm going to choose 110 as the left side radius coming into the roundabout. And that turns out something like this. You may also recall that we talked about the range of exit radii at the edge of the roundabout being between 150 feet and 500 feet. I like to start with 400-foot radii, so I'll put in 400 on the outside, and then again I add the 20 feet, so I'll tie 420 in there, and that results in entry and exit lanes and the splitter island that looks something like that. Now, as we transition back toward the beginning of the approach or the western leg, we've got to get from this 20 to 24-foot width at the roundabout back to 12-foot lanes and whatever the existing shoulder width is. A lot of times we know we need the 20 feet to pass a stalled vehicle. So in this section, I may choose, when we're adjacent to the splitter island, I may choose 16 and 4 to get that 20-foot dimension. And I'll extend this arc something like that. Similarly on the exit side. Something like that. I'll trim those up. I had pieced in the northbound approach earlier, so we can look at what a radii might be to tie in to the exit side. And I may choose a 60 to start. Now all of this will need to be refined by our fastest paths and our truck turning movements. So this is just a guess based off of experience, but we will need to verify all of these dimensions with our performance checks. I'll offset this to 2-foot gutter pan width and the width of the curb. Do the same on this side. Do a little bit more cleanup, getting rid of some of this extra curve on the central island. Oops. And so that's quick and dirty how I develop my approach roadways. You can begin, you can determine where you want the 16-foot lanes to end or begin to transition back to 12. A lot of times I like to carry that width through the splitter island, and then as you taper back to existing conditions, you also handle that width taper as well in this area. So how does this compare to the examples that we had on the screen previously? If I attach the concept that we discussed in the first part of the sketching, you can see that on the entry side, we match up pretty well with the concept that had been drawn previously. Now that concept was done prior to the current GDOT guidance related to these high-speed approach transition zones. And so you can see that the original design was done pretty well and was pretty close to in accordance with the GDOT guidance, um, even without the guidance. The main difference on the exit side is that I had provided the 15-foot splitter island envelope, which was much wider than what was provided in the original concept. And just a point there is that this is a residential house and they have a driveway. And if I zoom in, you can see the driveway break in the splitter island. And there a 15-foot wide median or splitter island in that area would be pretty wide uh, for someone trying to turn in and out. So there is some benefit to narrowing it up. It helps make it easier to get in and out of that driveway. It also may have been a practical design consideration trying to reduce the amount of widening or construction costs. Similarly, on the exit side, um, again, this is a more narrow right of way. So this splitter island is actually shorter, and this approaches a town, so the splitter island length was reduced because of slightly lower speeds and development that will be occurring in the area. Again, the entry side lines up pretty well. The exit side is significantly different due to the much wider splitter island. So on this leg, we may want to look at tightening that up as we look to refine our alternatives. But that's something we'll have to talk through as a design team after we evaluate the impacts and costs and any other considerations. And with that, that wraps up our sketching exercise for single lane roundabouts design basics.